Thank you for the introduction and for giving me the possibility to talk here. So as you already said, I'm going to talk about analytic conifold periods. This talk is based on the last paper of our group, together with Rafa Alvarez-Garcia, Max Brinkmann, and Ralf Blumenhagen, which actually just has been accepted for publication in Fortschritte der Physik. So why are we interested in analytic conifold periods? I'm going to work in a setting of type 2 string theory, compactified on a Calabi-Yau threefold with fluxes. These fluxes will break the usual n=2 supersymmetry down to n=1, and an n=1 theory can be described by a scalar and a superpotential, denoted K and W. These potentials, so the Kukow-Farber-Witten superpotential and the scalar potential, depend on the chosen fluxes and especially on the periods. So if you want to compute anything in our theory, we need knowledge of these periods. For the KKLT construction, which is the most famous de Sitter construction we have at the moment in string theory, small values of W0, so the value of a superpotential in the minimum, are required. There's a known mechanism how to obtain such small values of W0 at the large complex structure point due to Dimitas, Kim, McAllister, and Moritz from last year. And our idea in the group was to generalize the same mechanism to the conifold. So in this talk, I will give you the mathematical tools how to compute these periods close to the conifold. And we will have a second talk today by Max, who will talk about the generalization of the actual method and the algorithm to the conifold, and talks more about the phenomenology part. And also I should state that there's a closely related independent work which appeared on the same day as our paper by the original authors, Dimitas, Kim, McAllister, and Moritz, who had effectively the same ideas, but who used a bit of a different math approach, and I will point out the differences of the two approaches. So as a start, let me set the mathematical framework. We will be interested in Calabi-Yau hypersurfaces or complete intersection Calabi-Yaus in weighted projective spaces. To define the periods, we need to choose a symplectic basis, which I will denote gamma alpha, of the free cycles. We always have 2H1 plus 2 free cycles, so we will have as many periods. Then we need to integrate the unique holomorphic free form, here denoted by an omega, over these free cycles, and this gives us the period vector. To define the Calabi-Yaus, we will use the charge vectors L. So in principle, a Calabi-Yau is defined by, or can be constructed in toric geometry by choosing a polyhedra, doing the fine star triangulation and all this stuff. But in the end, this comes down that one obtains linear dependencies between the vertices of these polyhedra. And these dependencies are the charge vectors, and they are closely related to the generators of the Mori cone. So for this talk, I don't want to go into details of this construction because it's well known, and they are listed in literature and can be nowadays computed automatically, for example, using Sage. So I will just assume that we know the charge vectors of the geometry we are interested in. Now, if we have these charge vectors, we can derive a system of differential equations, the so-called Picker-Fuchs equations, which constrain the periods and actually find the periods. This system is a priori defined in the larger space than the physical moduli space, parameterized by these A0 to AS variables. But the real physical complex structure deformation we will be interested in, I will be noting xk, are actually uniquely defined by these the charge vectors L. So we have this system here, which actually was derived a long time ago. And the periods have a property that they are annihilated by these Picker-Fuchs operators. So we can write this Picker-Fuchs system around the large complex structure point or any point we want in moduli space using the correct coordinate transformations. So how do we now really compute the periods? In computing them directly in a symplectic basis is actually rather hard. So for the quintic or really easy Calabi-Yaus, you can solve the integral I gave earlier analytically, but actually it's much easier to solve the Picker-Fuchs equations in any local basis by just making a power series approach. So what one then does is, one knows what we have a finite vector space, and the periods we have are one basis and the symplectic basis is another. So we know that there's a transition matrix in between them, which is linearly. So we have this really simple relation between the periods in the symplectic basis and the local basis we can compute. So effectively, one always computes a local solution and then computes a transition matrix to get the symplectic basis. The problem is now we need this transition matrix. At the LCS point, which is defined as a point of maximum unipoint monotony, which is actually easy because this monotomies fix the transition matrix uniquely. But if you move away from this point of maximum monotony, we no longer have enough monotomies to actually fix this matrix uniquely, so we need some other method. And the only known method really is to actually compute the symplectic basis at the large complex structure point and analytically continue it to any other point in the moduli space and compute the transition matrix between this point and the large complex structure point. So this is a bit complicated, so it's easier to show this on a picture. So here on the left-hand side, I have a large complex structure point. On the right-hand side, I have the conifold. As the local basis, I denote with the small omegas, can be computed by a power series approach in both points. So these are the small omegas we know. As I said, in the large complex structure, we have enough monotony to fix the transition matrix to the symplectic basis. For our paper now, we were interested in the periods at the conifold. So we are actually interested in the symplectic basis over here. Here, we cannot compute this matrix M2 because we don't have enough monotony. So what we do is we take the local basis at the large complex structure point, we analytically continue it over to the conifold, expand it in a power series around the conifold. At the conifold, we already have a power series. So all we have to do is match the coefficients of each term in the power series to get a transition matrix M. And now it's easy to get this transition matrix because this transition matrix is just the product of a transition matrix to the RCS and then up to a symplectic basis, because there's only a unique symplectic basis, so this to this is just the identity. And in the end, we have this transition matrix we are interested in and can compute the symplectic basis. So let me get into detail how each of these steps work. First, how do we compute the local basis? As I said, these Becker-Fuchs equations can be solved by a power series ansatz. This ansatz looks actually quite horrible, but it's really simple. With J, just label the 2h to 1 plus 2 different periods we have. And for each of these periods, we make a power series ansatz in x and log x. So this is just all possible combinations. The k label possible appearance of a log x. In a threefold, this is at maximum 3, so k runs from 0 to 3. While the I are just the power series of the x coordinate. So this is just the usual power series running from 0 to infinity. And these coefficients in front are just constants, which we now can determine order by order. So we plug in this ansatz into this equation, which are just derivatives of x and log x, so it's easy to compute, and order for order solve these equations, determining theCijk, and we have a local basis. So this is easy. At the RCS, it's even easier, because one can write a closed form, where by closed I mean an infinite series, which was already given by Hosono, Clem, Tyson, and Yau in '93, so a long time ago. This solution looks actually horrible, but it's just, again, a power series now with the logs replaced by a gamma function. And it depends only on the complex structure coordinates, the charge vectors from earlier, and some so-called indices rho I. These rho I are just introduced that one can write down the complete basis in an easy way. The way this works is one defines derivative operators with respect to these rho I. They are up to third order, so first, second, and third order. And then the whole period vector is just given by this fundamental period I had on the slide before, and these derivative operators acting on them. And once one has computed all these derivatives, the last thing one has to do is set all these rho I to 0. And that's it. But now we need to analytically continue this local basis at the LCS. So with local basis, I mean exactly these expressions here, to the conifold. There are many methods how this can be done by now. The historical version is to do it numerically. This is like most people have done it. I listed here some papers, but I most likely missed a lot because everybody was doing that. But there are more involved methods. For example, there's a generalization of Norlund's method developed by Manuel Scheidegger in 2016, which uses a certain recurrence of infinite series. One could also use the polylog structure of the superpotential, which is what actually Dimitas, Kimek, Alistair, and Moritz did in the paper appearing together with ours. Or one could use epsilon expansion of hypergeometric functions and computing closed form of these. And this is what we did in our paper. And the most involved of all methods would probably be to use the so-called KSC conjecture after the authors Clem, Schlechter, and Sagi. But this is actually to this date unpublished. I checked this morning, so I will be rather short about this. Let me go through each of these methods step by step. The numerical method is the most easy one. You just take the local bases you have and go to an overlapping region of convergence and expand both bases in a power series around this overlapping point. And then you compare the coefficients and get equations for your transition matrix. That's extremely easy to use, but you get only numerical results. But for most applications, for example, if you want to check the distance conjecture in the moduli space, this is more than enough. There are two disadvantages to this method, though. First, the results depend on the chosen point. If you move the point just by 10 to the minus 5, the results, so the entries of a transition matrix, can actually vary by the percentage level, which is horribly, especially if you want to see some cancellations. And moreover, for our algorithm later on, we need certain rationality properties of a prepotential. If you just have numerical results, you get an enormous amount of small numbers, and you cannot decide if these are 0 and actually canceling, or if it's just some really, really small number. So you can never say, if you just have a numerical number, if this number is rational or it's transcendental. So for our method, this method was not good enough. So Nolan's method of Scheidegger is actually quite closely related to our work. What he does is he takes a hypergeometric function and analytically continues it to argument 1. This only works in a 1-parameter case, and it works recursively. What he does is he takes a PFQ function and rewrites it as an infinite sum of a P-1, Q-1 function, and does this until he hits a 2F1 function, where then he can use Euler's reflection formula to get a result. The result is therefore an infinite sum of PFQ functions. This is really useful for numerical evaluations because you get rid of the point dependence of the pure numerical result. And in some cases, you can even get analytic results if you can resum this method. This is especially the case for tori or K3 surfaces. But for a full 3D Calabi-Yau, you don't get it. Moreover, you can only do it in a 1-parameter case, so for like the quintic or the sextic, but you cannot do it in a multi-parameter case, so it's not that useful for us. Now to the method of DKMM, which is just using the properties of a polylogarithm appearing in the prepotential. At the LCS point, the prepotential is known since a long time, since back to Candelas, to be given by a cubic polynomial, the theta-free correction, and an infinite instanton series. This instanton series can actually be written as a sum over curves and a certain polylogarithm, so here d logarithm. And now again, we can use Euler's reflection formula to rate the d logarithm at x to the d logarithm at 1 minus x, and therefore getting rid of all these divergences and doing the analytic continuation. This is extremely elegant and allows the evaluation of a prepotential for certain shrinking curves, as long as the curves lies outside the interior cone, such that this sum here actually terminates. This does not allow to compute the full period vector, because we cannot compute the period which is dual to the fundamental period. This period is related to the overall volume, and so all curves contribute. So this argument that we choose a curve outside the interior cone does no longer work. But it gives us the full superpotential if you do not put any fluxes on this period you cannot compute. So if you just want to find a small superpotential, like DKMM wanted, this is a perfectly fine method, and it's extremely elegant because it's short. We, on the other hand, wanted the full scalar potential and the Kähler potential, so we needed all periods, even the one dual to the fundamental. So how do we get that? This needs much, much more mathematical machinery, sadly. Namely, the so-called epsilon expansion of hypergeometric functions. If we go back to the expression at the large complex structure point of Hosono, Clem, Tyson, and Yau, we can actually perform one of these summations analytically. So we have, for example, here for the 3 moduli case, the 2 moduli which were not resummed, Normally here is a third sum from n3 from 0 to infinity and set to the n3. But this set dependence can be resummed into a hypergeometric function. In front of it, there's some general combination of gamma functions, which is coordinate independent. Later on, we will need derivatives of this to compute the transition matrix. Derivatives of gamma functions are just polygamma functions, and evaluating them at 1 or some integer numbers is not any problem. So this function here is trivial. The only problem for analytic continuation lies in this hypergeometric function. And we need up to third derivatives with respect to the parameters rho, and they then need to be able to expand this function in Z around 1. And so we need the full epsilon expansion of this hypergeometric function. These epsilon expansions are well studied in the amplitudes community. If you want to compute any Feynman amplitude, you will, if you go to enough loops, end up in hypergeometric functions. So these guys really studied this in detail. Recently, there's even more progress in the math community by actually evaluating these values of hypergeometric functions at 1 analytically. Especially this guy, Jack Dorizio, I want to point out, because he was able to find closed forms only in terms of elliptic functions, which gives extremely simple and easy to handle expressions for these hypergeometric functions. So what are these hypergeometric functions I'm talking about all the time? They are defined by two parameter vectors, a and b, of length p and q. They are then defined by an infinite sum of Pochhammer symbols, where the a vectors goes in the nominator and the b vectors goes in the denominator, and one has an exponential sum, so x to the n over n factorial. For Calabi-Yau hypersurfaces, actually only one class of hypergeometric functions matters, and this is where p is exactly 1 larger than q. This is due to the Calabi-Yau condition. And this is rather obvious, but the more parameters we have, the more complicated this sum here becomes, and the harder the evaluation will be in the end. Some examples for that. An hypergeometric 1f0 is actually trivial. It's just a single monomial with a parameter appearing in the exponent. If you go to 2f1 functions, we have a closed form available for all possible values of a and b. So these functions are actually solved. For 3f2, the situation is not as nice. Now we have only integer or half integer parameters we can solve and have a closed form for. And this is the first case which is interesting for geometry, because shrinking curves are actually resulting in 3f2 functions. If you go to higher divisors, as for example shrinking divisors or shrinking Calabi-Yaus, we will end up in 4f3 or higher. And here only closed forms are available for integer parameters and some special values which mathematicians have been able to compute. We were mainly interested in shrinking curves, so for us the 3f2 case is enough. And what is really nice, this is already implemented in the so-called hypx2 package of Mathematica. So once you have installed this package, Mathematica is able to compute all of these 3f2 functions we need in closed form. So now, how does this relate to geometry? We have these hypergeometric functions with parameter dependence, and we have the charge vectors. If you play around with this a bit, you really soon realize that the charge vectors enter the parameters inversely, which means if we have an entry in the charge vector of 5, we will get a 1 over 5 in the parameter. We can only deal with rational parameters up to 1/2. So, which means if you restrict the charge vectors entries to be smaller than 2, we only get half integer values in the hypergeometric function, and this is solvable. So, for example, these two charge vectors here, the first one describing a P1, are really easy to solve in the method, but these here are much harder. Actually, what is quite interesting, -3 is much, much harder than -4, because this gives 1 over 3 as a parameter. And these functions in the end are related to Borwein theta functions, while this here is related, because of the work of Jack Dorizio, to elliptic functions. So this is actually easier to do with this. But after all this pre-talk and math, let me get to an example of what we will use in our paper. For the P112812 hypersurface in weighted projective space, we get these charge vectors. You see, the second and the third line have only 1s and 2 in them. So these will result in half integer hypergeometric functions. So these two are solvable. This one will result in a 1 over 6 parameter. So this one is really hard. And it's actually not even a shrinking curve, but a shrinking divisor. Also, I have given here, just for completeness, the Picker-Fuchs system, which we will use to solve the local basis around the conifold. Now, when we take our general expression for this special Calabi-Yau, the hypergeometric function I have listed before takes this special form. As I promised, it's only half integer parameters. So for any value of n, we can compute this function. So if you want to compute the transition matrix, we just take the first 2 or 3 terms of this sum and of this sum, which gives us in total 9 terms. This then gives us 9 hypergeometric functions with half integer parameters. And we now feed this into the hypx2 package to get hugely complicated expressions in terms of harmonic polylogarithms. These harmonic polylogarithms are generalizations of the usual polylogarithms. The exact form is not important. They are defined by some integrals over functions. The important thing is that the derivatives and the power series at one of these functions are known. So what we need for our computation, everything is known, and we can just put it into Mathematica to get an expansion around the conifold of this 3f2. Now, the only thing we need is a local solution around the conifold. So don't get scared, this is a horrible expression. All of these W tildes here are actually power series in the coordinates x1 to x3. But the important thing is we can just compare this to the epsilon expansion we obtained here from our hypx2 package. And if we compare this, we finally get our transition matrix. This matrix also looks not so nicely. I mean, we get a lot of zeros and a lot of logs and high in non-rationality. So it looks like we didn't gain much from this computation. But if you compare this to the result of the numerical method, which we did for a cross-check, you see first that obviously they agree, which is nice as a cross-check. But moreover, you're now able to actually see what is canceling out. For example, if you take this fourth value here, if you take 1 point, you get a negative number. If you move the point by 10 to the -5 away from this point, you get a positive number of roughly the same order. So it's extremely hard to decide what this value is or if it's 0. But if you take the analytic result, you just see, okay, it's 0 and it's canceling out everything. Now, if you have these periods, we are finally able to compute also the transition matrix. We are now able to compute the periods. The local basis is really fast to compute to high order, like 30 plus. It's not a problem at all with modern computers. So now you just multiply this with a transition matrix, and you can compute anything you want. The basis is chosen really nicely, so the mirror maps are just given by dividing out the first period. And then you get everything, the scalar, the super, the pre, and the scalar potential, so anything you could wish of. Here, I just list the pre-potential, which Max later on will use for modular stabilization and phenomenology. So there you can see how you can apply this to actually using physics. Also notice most of these non-rationalities we had in the transition matrix, like all these logs and so on, cancel out. The only non-rational terms which are still remaining are in the quadratic coefficient of the conifold modulus, here denoted by Z, and of course the theta-free correction, which already was there at the large complex structure point. So here, I'm not going on about the phenomenology. I'm going to comment a bit on what would we need to generalize this method to higher geometries. So if we want the general shrinking curve and got rid of this restriction of the charge vector only including values smaller than 2, we would need 3f2s with general parameters. If we would to go on to shrinking divisors or even shrinking Calabi-Yaus, we would need higher PFQs with p larger than 3. The nice thing is the exponent expansion is for all of these cases actually known, which was solved by Granat and Zesma already back in 2013. The result of this algorithm of Granat is that you get higher PFQs out for the derivatives. So for example, the parameter derivative of a 3f2 is given by a 4f3, or even worse, by some infinite harmonic or Euler sums. So this reduces the problem to a number theoretic problem. For the case of 3f2 or the general shrinking curve, actually it's proven by mathematicians now that the results always lie in the so-called weight 4 colored multiple zeta values. This is some group of function values. The nice thing is there's a basis of transcendental numbers which can appear here. For 4f3, the situation is not nearly as nice because one gets so-called critical L values of Hecke eigenforms. Due to time, I will not be able to go further into what actually these functions are. I will just give a really short example, which is 4 quadratics in projective space 7-dimensional. There, the fundamental period is the most easy for free possible. It's just 4 times 1/2 and 3 times 1. And Rogers, Venn, and Zucker have computed this value at 1 to be given by exactly one of these critical L values of some Hecke eigenform. This is actually in agreement with the so-called KSC conjecture by Clem, Scheidegger, and Sagier, which state that all entries of transition matrices are given by some of these L values. For us, what these values is not really important, but what's important is that ratios of them behave really nicely to be turning out to be algebraic numbers times some pi factors. And even better, this algebraic number is often rational. So for our algorithm, we would need rational numbers here. So this is perfect for us. As a final comment, it's also a possible application of machine learning. The evaluation of these PFQs at 1 is really complicated, but there's a huge amount of structure in them. So if you take all possible PFQs up to 4 or 3 with parameters in this set here, you get 268,000 functions, but only 288 different values. So this is a huge data set. There are many structural relations, and it's a high-dimensional parameter space, which you can hardly plot, but a neural network is perfectly suited to learn such things. So it would be an interesting thing to look into it if we can actually apply machine learning to this. In the 3f2 case, it's even better. As I already said, we know a base of this colored multiplicity values, so we can actually use integer relation algorithms to identify the closed forms if you just have the numerical values, because we only need to compute the coefficient vector of the spaces and not the real functions like some zeta function, logs, and so on. As an example of this is this really absurd identity, which is the most absurd I actually known of. It's a 23 parameter hypergeometric function, which has a closed form, which was purely guessed by these integer relation algorithms. So this machine learning techniques could be really interesting. So let me sum up. What I wanted to tell you is that we compute the periods at the conifold analytically using closed form of hypergeometric functions. For shrinking curves, this is already doable, and we used this in our paper. And in principle, these are computable for any manifold you could wish for. But the generalization requires rather deep number theory, which at the moment is developed. See, for example, this upcoming paper by Clem, Scheidegger, and Sagier. And finally, machine learning could help us to find these hidden structures of these hypergeometric functions we at the moment don't know, and simplify many of these computations drastically. That was everything I wanted to say. Thank you for your attention.
All right, Lorenz, thank you for the very nice talk. We can all thank Lorenz using our clap emoji. While we wait for other questions to come in, you probably already explained this pretty well, but let me just ask again, can you state what in your method relied being around a conifold point?
So the goal was to compute at the conifold. So the conifold is special as it's the single point where all of these hypergeometric functions are only conditionally convergent. So if you want any finite point in the moduli space, the computation is actually much simpler because you can just take your series and compute with the series because it's absolute convergent outside of the conifold.
Oh, very nice. Okay, so this method generalizes easily to generic points in complex structure moduli space, but the conifold is much more challenging.
Exactly.
Got it. Okay, thank you. All right, are there any other questions? Okay, if not, let's thank Lorenz one more